Hello! This will be a demonstration of Proposition 11 from Book 9 of Euclid's Elements, which says that if numbers be in continued proportion beginning from the unit, then the lesser number measures the greater number according to one of the numbers between them. We have four numbers b, c, d, and e, which are in continued proportion beginning from the unit a. So the unit a is to b, just as b is to c, just as c is to d, and just as d is to e. What we want to prove is that the lesser number b measures the greater number e according to one of the numbers c and d which lie between them. Put another way, that there are as many b's in e as there are units in either c or d. That is what it means for one number to measure a second number according to a third number. That there are as many units in that third number as there are of the first number in the second number. So, we know that the unit a is to the number b, just as the number d is to the number e. We were given that from our continued proportion. And we know, of course, that the unit a measures the number b, for the unit measures all numbers. Which then means, by the definition of proportionality, definition 720, that the unit a measures the number b the same number of times that the number d measures the number e. We can also alternate this statement about equal measuring by proposition 715 and say also that the unit a measures the number d the same number of times that the number b, measures the number e. Put another way, that there are as many b's in e as there are units in a. But this is what it means for the number b to measure the number e according to the number d, that there are as many b's in e as there are units in d. And having shown that the number b measures the number e according to the number d which lies between them, we have proved that which we set out to prove, which means we're done with the proposition, therefore, etc., q, e, d. There is a porism appended to this proposition that specifies which of the numbers between the measuring number and the measured number is the one according to which the measuring number measures the measured number. I don't want to say the word measured one more time, but I'm going to have to. What this porism says is that whatever place the measuring number has from the unit, the same place has the number according to which it measures backwards from the measured number. This is one of those propositions where the porism is actually more important than the proposition. You'll often see this porism cited alongside the proposition. So you'll see proposition 9.11 and the porism to proposition 9.11. You'll see them together because this porism is very important. Here's what it tells us. Say we have a continued proportion beginning from the unit. We'll just do the powers of 2. This is a nice example. So we obviously start with 1, that's our unit. We then go to 2. Then the next power is 4. The next one is 8, and we'll stop at the next power, which is 16. These are the powers of 2. We've gone through these before. What this proposition tells us is if we want to know how many times 2 measures 16, or according to what number 2 measures 16, here's what we do. We figure out how far away our measuring number 2 is from our units. We start from our unit, we do one hop like that. So because there is one hop between the unit, or from the unit, to the measuring number, we start from the measured number, which is 16 here. We do one hop backwards, we land on 8, and this tells us that 8 is that number according to which 2 measures 16. 2 measures 16 according to 8. Put another way, 16 divided by 2 makes 8, or if we want to say this about multiplication instead, 2 times 8 makes 16. You can, of course, do this sort of process of counting hops no matter where you start. So say we start at 4 instead. And I want to know how many times 4 measures 16. Just to clarify, it doesn't have to be 16. It doesn't have to be the last one. We can do how many times 4 measures 8, and the proposition will still do its thing. But say we want to know how many times 4 measures 16, or according to what number 4 measures 16. What we do is we start from the unit, and we figure out, okay, how many hops away is 4 from our unit? 1 hop, 2 hops. So it takes 2 hops to land from the unit to 4. What that tells us is we're going to start from 16, do 1 hop, 2 hops backwards, And the number that we land on is the number according to which 4 measures 16. In this case, it's also 4. So 4 measures 16 according to 4. Put another way, as a statement about division, 16 divided by 4 is 4, or about multiplication, 4 times 4 makes 16. We can do the same thing if we start from 8. So we say we want to know according to what number 8 measures 16. What we do is we count how many hops it takes to get from the unit to 8. It takes 1 hop, 2 hops, 3 hops. So what that tells us is we start from 16, do 3 hops backwards, 1, 2, 3, we land on 2. What that tells us is that 8 measures 16 according to 2. In other words, 16 divided by 8 makes 2, or that 8 times 2 makes 16. Those are all just 3 different ways of saying the same thing. Put more generally, this allows us to do division within continued proportions. So how many times a greater number is divided into a lesser number, this is how we would do that. What this also lets us do is to get another one of those exponent rules. So you'll remember in Proposition 9.3, if you've watched that video, of course, at the end there, I talked about a general exponent rule you can get from the square of a cube number also being a cube number. Now, just like that proposition, we can get another exponent rule from this one. Not the same one, but a more important one. This one allows us to get the rules surrounding multiplication and division of same base powers. What do I mean? Well, the exponent rules I want to explain here are a, if we have any base a, we raise that to some power m, we multiply it by that same base raised to another power n. What do we know about this? Well, what we know about this is that a is equal to the sum of the exponents. So a to the m multiplied by a to the n gets us a to the power of m plus n. So as a specific example, say we had 2 to the 2 multiplied by 2 to the 3. That is equal to 2 to the 5, because 5 is 2 plus 3. And that checks out. 2 to the 2 is 4, 2 to the 3 is 8, their product is 32, and 2 to the 5 is 32. So that checks out. This is similar to the rule surrounding division, right? So if we have a to the m, divide that by a to the n, what we do instead is not add the exponents, but we subtract them. So a to the m divided by a to the n is equal to a to the m minus n. Now, you might be asking yourself, where am I getting that from the proposition? Well, where I'm getting that from is the general formula for continued proportions, which begin from the unit that we laid out in Proposition 9.8. Hopefully you remember how that goes. If we start from the unit, like that, then a continued proportion will go as follows. We'll have a to the 2, a to the 3, and we just keep increasing the exponent by 1. We found this out in Proposition 9.8, and we can, do this for however long we like. If we do it this way, the rules about exponent multiplication and division, or same base multiplication and division, I should say, are found more easily. So say we wanted to know how many times a squared measures a to the 5th, or in other words, what a to the 5th divided by a squared makes. Well, what we would do is we would count how many hops it takes to get from 1 to a squared. 1, 2 hops. Then what we do is we start from a to the 5th, do 2 hops backwards, 1, 2. We land on a cubed. What that tells us is that a to the 5th divided by a squared gets us a cubed. And this is where we get the rule about division from. Because you'll notice that 3 is just 5 minus 2. And this process of counting hops away from the unit and the measured number, this is the same as just subtracting the exponents, but Euclid doesn't have the language of exponents, so he has to put it in this way about position from the unit and from the measured number in this kind of clunky way, I'll say. But with exponent notation, it becomes more clear what exactly it means to count hops. It means to subtract the exponents. And this rule about division of same base exponents, just the same as subtracting the exponents and raising the base to that power. What that then gets us is the statement, of course, about same base multiplication. Because we know that a to the fifth divided by a squared equaling a cubed, that's equivalent to saying that a squared times a cubed makes a to the fifth. Or in other words, a squared, or a to the 2, times a cubed, a to the 3, is equal to a to the 2 plus 3, or a to the 5. So that's where we get the rule from exponent multiplication from. It's just the other side of the division rule, right? These are just two sides of the same coin. Multiplication and division are nice like that. So as we saw in proposition 9.3, where you can generalize that proposition to get a certain exponent rule, you can generalize proposition 9.11 to get 2 more exponent rules, which is obviously incredible. That's very important. That's all I've got to say about this proposition. I hope I've explained its relevance well enough, and if I haven't, comment section is always open. So with that said, I'll end the video here and move on to proposition 9.12.